All right, so as I mentioned a moment ago, we are going to be talking about instantaneous power and average power today. No. No, I forgot an anius there or something. Yeah, let's move this over. Instant A-N, there we go. And let's put these guys back together. Does that look better? All right, sorry about that. Excuse me. So here's instantaneous power and average power. And so we are going to start our discussion in a very general case. So let's say that we have a source, Vs of t, and it is supplying power to our good friend, the linear black box network. Such that a voltage drop V of t appears across the terminals. Excuse me. And I of t flows into the network. And let's say specifically that V of t is of the form Vm cosine omega t plus theta v volts. And I of t is of the form Im cosine omega t plus theta I amperes. The instantaneous power absorbed by our linear black box network, or supplied by our voltage source in this case, will simply be P as a function of time is equal to the voltage as a function of time multiplied by the current as a function of time. So P is still equal to I times V. Because we have sinusoidal signals here, we can do some mathematical manipulation. So I could call this Vm cosine omega t plus theta v and multiply it by Im cosine omega t plus some phase angle theta I. I'm going to apply a trig identity that we did not talk about the other day. So I'm going to give it to you here. That says cosine angle 1 times cosine angle 2 is equal to 1/2 cosine angle 1 minus angle 2 plus 1/2 cosine angle 1 plus angle 2. So if we apply that trig identity, what we wind up getting is 1/2 Vm Im cosine theta v minus theta I. So our frequency dependence has gone away. Plus 1/2 Vm Im cosine twice omega t plus theta v plus theta I. So this instantaneous power is made up of two parts. This guy over here on the left, and then this guy over here on the right. So let's talk about this guy on the left first. Right? Vm is the magnitude of the time domain voltage drop across our network, which is the same thing as the magnitude of the phasor voltage across our network. What I'm trying to do here is reinforce the fact that we're still not going to analyze these circuits in the time domain because that's a huge pain in the butt. So we're just going to use our frequency domain analysis to come up with the different parts that get plugged into this equation. Okay. Similarly, Im is the magnitude of our time domain current and the magnitude of our phasor current. Theta V is the phase angle of our voltage in both the time domain and the frequency domain. And theta I is the phase angle of the current in both the time domain and the frequency domain. All four of those quantities are constant, which means 1/2 Vm Im cosine theta V minus theta I is also a constant. So we have some DC contribution on the left-hand side. And then on the right-hand side, we have an AC contribution because it still depends on omega t. But it's actually a double frequency term because it depends on twice omega t. So the oscillatory nature of the power happens at twice the frequency as the oscillations of the voltage and the current. Okay. So I'm going to call this a 2 omega AC contribution. So graphically, that might look something like this. Here is P as a function of time. Here is time. And here is that sinusoidal bit superimposed on top of a DC offset, right? So this level right here is what we would call PDC. This peak value would be PDC plus PM, which will be the magnitude of our AC portion of the power. And then we're going to have a negative peak down here at PDC minus P sub M. So this is a generic representation, okay, of the power that is absorbed, the instantaneous power that is absorbed by this linear black box network here, okay? So depending on what's inside the linear black box network, it's really just going to shift this graph up and down. That's the only thing that it could potentially do. But one thing that's very interesting here is that there are regions. I'm going to try to color this in a little bit. This region right here in this region right here, where the power absorbed by our linear black box network is negative in value. So what does that mean? It's our linear black box network here sometimes winds up supplying some power to the source. Right? So for this to happen, our linear black box network must have some sort of energy storage elements in it, like capacitors and inductors. Okay. For our graph to look exactly like this, we would have to have some sort of resistance too, and I'll explain that in a minute. Okay. So let's take a moment to look at that DC term for a little bit longer. Okay. So what do you think the DC term represents? Well, obviously it's the bit that doesn't change in time, but think about it, okay? We have a sinusoidal quantity, and exactly half the time our value is above this DC level, and exactly half the time it is below this DC level. Exactly right. The DC contribution of our instantaneous power is our average power. We could just as simply call this P average, which in this case would be 1/2 VM IM cosine theta V minus theta I. So another interesting observation here, and you guys were actually introduced to this concept on, I think, your first homework assignment in this class, way back on homework set number 1. What's the average value of the voltage drop across our network? Let me scroll up here so we have the mathematical relationship, right? What's the average value of Vm cosine omega t plus theta V? I disagree. It's not Vm, 0. It's a cosine function, right? So half the time it's above the horizontal axis. The other half of the time it's below the horizontal axis. Same thing for our current, right? So the average value of the voltage drop across our network is 0. The average value of the current flowing through our network is 0. But the average amount of power that is delivered to our network is non-zero. So dealing with power in AC circuits is a very important topic because it actually tells us a lot of information about how our system behaves, because not everything trends to 0 on an average, looking at it on the average, okay? All right, so we have this generic equation that technically works for anything. As long as we know the voltage drop over our element or network of interest and the current flowing through our element or network of interest, we have a means by which we can calculate the instantaneous power and a means by which we could calculate the average power. Tyler. Okay, fantastic question. So if I apply the trig identity I've written here in blue, angle 1 that I'm looking at is omega t plus theta v, right? So when I have omega multiplied by t, that's something in radians per second, multiplied by time measured in seconds gives me an angle. If I add a phase angle to that, then that's just angle plus angle equals angle, right? So angle 1 is omega t plus theta v. Angle 2 is omega t plus theta I. When I take the difference of those, I have omega t plus theta v minus omega t minus theta I, and the only part that survives is theta v minus theta I. Good question. All right, so let's take this generic equation and develop some relationships for resistors, capacitors, and inductors specifically, okay? So for a resistor R, we know a few things, right? We know that the magnitude of the voltage Vm is equal to Im multiplied by R. And we know that theta V is equal to theta I. Right? There is no phase shift introduced whenever we have a purely resistive quantity. All right. So we could say that the instantaneous power absorbed by a resistor is going to be 1/2 Vm Im. So when we do that cosine theta V minus theta I bit, what's that going to go to? So what's theta V minus theta I for a resistor, Jenny? 0. So it's cosine of 0, 1. So we're just going to have 1/2 Vm Im and then nothing, right? So 1 plus, and now we're going to have our double frequency term. But actually, hold on. Let me write this in a different way. So 1/2 Vm Im plus 1/2 Vm Im cosine twice omega t plus theta V plus theta I. But I can simplify this, okay? So this could be 1/2 Vm squared over R times 1 plus cosine twice omega t plus twice theta V. So this would be a form where all I need to know is the voltage drop over the resistor, and I can calculate the instantaneous power. All I've done is simply substitute the fact that Im multiplied by R gives me V, or another way to put it would be V is equal to, Im is equal to V over R. So I just made that substitution there. And because theta V and theta I are equal, I can just lump those two guys together and call it twice theta V. And very similarly, I can say, I could express the average power absorbed by a resistor as 1/2 Im squared times R multiplied by 1 plus cosine twice omega t plus twice theta I. So I have a means by which to determine my instantaneous power absorbed by a resistor purely in terms of the voltage drop over the resistor or the current flowing through the resistor. I no longer need to know both pieces of information. That's a kind of handy dandy tool, right? What's the average power absorbed by a resistor? So for our generic form up here, we said that the average power was just the DC contribution. That works for everything. So the DC contribution of these guys is literally the average power. So this would be 1/2 Vm times Im, which is the same as 1/2 Vm squared over R, which is the same as 1/2 Im squared multiplied by R. So it's literally the exact same relationships that we got in DC circuits, except that there's a factor of 1/2 that comes from the fact that we're multiplying those two sinusoidal quantities together. Any questions regarding a resistor? Hopefully fairly straightforward. All right. Now let's talk. Yes, ma'am. Let me scroll back to it.
Yeah, but you need to see average. Where does the cosine function here?
Okay, so that's a fantastic question that we could get into in just a second. Okay, so what we observe here qualitatively was that the DC portion of our waveform is simply the average value. But let's mathematically explain it just for the sake of argument, because I think this actually might come up on your homework. So let's pump the brakes on this for just a second before we get into inductors and current and talk about the average power specifically. Okay, so let's say that x of t is a periodic quantity. With period capital T. How would I go about finding the average value of a periodic quantity? Anybody remember this from probably your pre-calculus? Getting a lot of blank stares. That's okay. X average is defined if we take our function x of t and we integrate it over exactly one period, and then we multiply that result by a factor of 1 over t. So we integrate the signal over one period, and then we divide by the length of the period. This gives us our average value. Does that make sense fundamentally? All right. Excuse me. So for our average power, that would be 1 divided by the period, the integral over one period of 1/2 Vm Im cosine theta v minus theta I plus 1/2 Vm Im cosine twice omega t plus theta v plus theta I. This whole thing integrated with respect to dt. I'm going to break this guy down into two integrals. So the first will be 1 over t integral from 0 to t of 1/2 Vm Im cosine theta v minus theta I dt. And then I'll also have a 1 over t integral from 0 to t of 1/2 Vm Im cosine twice omega t plus theta v plus theta I. Let's talk about the first term here. Everything except for dt is literally a constant, right? So this would look like 1 divided by t multiplied by 1/2 Vm Im cosine theta v minus theta I times the integral from 0 to t of dt. So what happens when I integrate 1 over any extended period of time, and then I divide by the duration of that time? It's just 1, right? So the integral of 1 multiplied by that 1 over t term just gives me 1. So all I'm left with there from this contribution is just 1/2 Vm Im cosine theta v minus theta I. But we do have this other AC part that we need to think about, all right? So I'm integrating this function over exactly 1 period. So what I'm doing, let me draw a little picture here. Here is PAC as a function of time. Here's time. Integrating this guy, if I had a particular phase angle, theta v plus theta I, all that would do would be shift this guy left or right, depending on what the phase angle is, but it wouldn't have anything to do with the amplitude at all, right? So if I'm integrating this guy over exactly 1 period, what happens when I add this area in orange above the horizontal axis to this area in orange below the horizontal axis? They cancel each other out completely, right? So we know that this whole guy right here, oops, my hand made it move out of my way too fast, goes to 0, which means our average power mathematically is literally exactly what we figured out to be qualitatively. Okay. Does that help answer your question?
Yes, I was wondering where the cosine went, but since theta v and theta I will
Right. Oh, so you were looking for something much more simple than what I just said. I'm sorry.
but I learned
Okay. Well, that's useful, I guess. I'm sorry for way over explaining, Justin.
What does that say? PL?
PAC, because we're just looking at the AC contribution of the power. Sorry for going way overboard, Hannah. All right, so let's circle back around to looking at what happens with an inductor. So for an inductor L, we know that the relationship between the magnitude of the voltage and the current is Vm is equal to omega L multiplied by Im. And we know that theta V is exactly equal to theta I plus 90 degrees. So the instantaneous power absorbed by an inductor is going to be 1/2 Vm Im. So what happens when we do cosine theta V minus cosine theta I, right? So we could say that theta I is the same as theta V minus 90 degrees from this representation, right? Just move the 90 degrees to the other hand side. And so theta V minus theta I looks like theta V minus 90 degrees, which is just the cosine of positive 90 degrees. What's the cosine of positive 90 degrees? 0. So that means that our DC portion goes away. An inductor does not absorb any average power, okay? That's a very interesting revelation because that means exactly half of the time the inductor is absorbing power and exactly half of the time the inductor is supplying power back to the source, which is a portion of why we see our black box network may supply power to the source. Anytime we have inductance, it spends literally half its time, exactly half its time, absorbing power, and exactly half of its time sending that power right back to where it got it from in an AC system. So 1/2 Vm Im times 0 plus 1/2 Vm Im cosine twice omega t plus theta v plus theta I. Now to express this in terms of only the voltage drop over the inductor, that's going to look like 1/2 Vm squared over omega L times cosine of twice omega t plus twice theta v minus 90 degrees, or 1/2 omega L times I squared cosine twice omega t plus twice theta I plus 90 degrees. And let me scroll up here real quick. PL average. Okay, just making sure I'm using the same basic notation. What is the average power absorbed by an inductor? Literally said it like 45 seconds ago. 0. Any questions regarding this guy? There's no DC contribution in the instantaneous power. Right? So the instantaneous power absorbed by anything is 1/2 Vm Im cosine theta v minus theta I. Theta v minus theta I for an inductor is exactly positive 90 degrees. Since the cosine of positive 90 degrees is 0, that whole DC term must be 0, which means the inductor does not absorb average power. All right, let's talk about a capacitor. In a capacitor, we know that Im is equal to omega c times Vm. And we know that theta I is equal to theta v plus 90 degrees. And all of these results come from when we developed our phasor or frequency domain relationships for capacitors, inductors, and resistors. The average power, or excuse me, the instantaneous power absorbed by a capacitor would be 1/2 Vm Im cosine theta v minus theta I. So in this case, since theta I is equal to theta v plus 90 degrees, we would have theta v minus theta v plus 90 degrees. So theta v minus theta v open parentheses plus 90 degrees or whatever. Effectively, we wind up getting cosine of negative 90 degrees in that term, right? So what's the cosine of negative 90 degrees? It's also 0. So our capacitors also don't absorb any average power. And then we would have 1/2 Vm Im cosine twice omega t plus theta v plus theta I in general. And using our relationships for the magnitude here, repeat your question. So the AC portion of the instantaneous power will always be at twice omega t. And it has been, let me make sure I didn't make a mistake here. No, yeah, so the AC portion of all of them has always been twice omega t plus theta v plus theta I. So I'm just carrying that through for the resistor here, where we just said, okay, so because of the relationship between Vm and Im, we can express everything, Vm and Im, theta v and theta I, we can express everything in terms of the voltage or the current. Same thing down here for our inductor, and now we're repeating the same procedure for our capacitor. So, excuse me, since omega c Vm is equal to Im, in terms of our voltage, we'll just have omega c Vm squared times the cosine of twice omega t plus twice theta v plus 90 degrees. Excuse me. And finally here, in terms of our current flowing through our capacitor, this is going to look like Im squared divided by omega c cosine twice omega t plus twice theta v, excuse me, plus twice theta I minus 90 degrees. And to repeat, the average power absorbed by a capacitor, PC average, is also 0 watts. So this is, Brandon, what's up?
So, and then a circuit with a capacitor and an inductor, while the inductor is supplying power, the capacitor is absorbing power.
If you only had a capacitor and an inductor, yes, that's what's called an LC tank or a resonant circuit. And effectively what it does is it just transfers the energy back and forth between those circuit elements forever. If you have a resistor in there, then that resistor gradually converts that energy into heat. And we'll learn all about RLC circuits in circuits 2, which I believe you're taking next quarter. Yeah, you're absolutely right. So with only a resistor and inductor, the energy storage cycle and discharge cycle are exactly 180 degrees out of phase. So they just dump energy back and forth between each other. That's a perfect way to think about it. All right, that's all I wanted to talk about for today, okay? There is an in-class assignment which has 3 problems. The one thing that I want to make you guys very aware of, because you're gonna get frustrated that you're getting the wrong answer, is the fact that when you're plugging numbers into this equation, twice omega t represents an angle that is expressed in radians. Theta v and theta I are angles that are expressed in degrees. So you need to use a conversion factor to make them both in radians or both in degrees, or else your answer doesn't make any sense. Other than that, it's literally just plugging stuff into these equations. If there's any circuit analysis to be done, do it in the frequency domain, because that contains all of the pieces of information that we use to put into these equations. Joshua, do you have a question? So omega, by definition, is a quantity that is measured in degrees, or excuse me, radians per second. And when we multiply that by time, that obviously gives us an angle in radians. So to convert twice omega t into an angle in degrees, simply multiply it by a conversion factor of 180 degrees per pi radian, and that gives you an angle in degrees. So to make that real explicit, I'm going to do it in red. I'm going to say multiply by 180 degrees over pi. And I will leave that up for the remainder of the class period. All right. Unless anybody has any questions, let's get cracking on that in-class assignment. Maybe duck out a little bit early.